Good morning. I just want to finish up the middle and high school chemistry, mainly because my son is at school up there in Brooks, and I just want to wrap this up. So, because I'm not a chemist, I'm a physicist, maybe a mathematician, maybe a philosopher, maybe other things, but chemistry, no, but I know a little bit about it. Okay, so I want to learn how to name compounds and write chemical formula, and keep the periodic table in the back of your mind also, always. It was there in my last talk. I took it off the board because you now memorize it, right? You know that the alkali metals are all in the first row. They have one outside valence electron. They behave all the same way in compounds. The next row in. The alkaline earth metals. Sodium is, I guess, what's on the top of the alkaline metals? I forget. Lithium, sodium, potassium, rubidium, cesium, and francium is the column down. So I guess lithium is on the top. Calcium and magnesium are two in the second row. They all have two outside valence electrons, so they behave in, well, you'll see in a minute. And then we go down through the transition metals. They're all in there in that lower block in the middle. And then we head over to the groups with carbon, nitrogen, oxygen, and so on at the top. Oxygen needs two outside electrons to be full, complete. Carbon is in the middle. Same way as silicon. Carbon has four outside electrons, so it can give or receive, so it makes very special strong covalent bonds. Look at the compounds of carbon I talked about when I did organic chemistry. Now, when I did organic chemistry, I just did the alkanes and then I stuck things on them at the ends to make alcohols and acids. But I never mentioned alkenes or alkynes. An alkene would be where you have a double bond between two carbon atoms, and an alkyne where you have one triple bond between two carbon atoms. Maybe I'll talk about those later. And then there are circular bonds such as, benzene, and there's more I can talk about in organic chemistry that you guys should know about. It's general knowledge that you carry away from you. I heard a chemist say, I guess it was my son's teacher, these boys won't need much more chemistry ever in their lives. Totally false, right? You really have to have a basic knowledge of chemistry in order to understand many things. The way your body works, your foods, what you eat, cooking, the things you find in the kitchen even, all right? Buying gasoline, what's octane? Octane is one of the alkanes that goes into gasoline. If you have a high octane content, it has a meaning, right? So let's talk about naming compounds. Now, there are two types of elements in the periodic table, generally speaking, metals and non-metals. And the only non-metals, most of the compounds, the things that take part in making compounds, will be mostly the non-metals. Metals plus metals, metallic bonds, that's just an alloy. They're not a compound as such. But non-metals, and here they are, hydrogen. I'm not going to list the inert gases, helium, neon, argon, krypton, radon, xenon in that column down here at the last, because they don't react with anything. They are inert. They're called noble gases, the inert gases. So I go hydrogen, nitrogen, oxygen, sulfur, chlorine, iodine, silicon. Anything else? I guess that's it. If there are others, they're rare. So for the non-metals that take part in all the compounds, these also make covalent compounds. Let's look at some covalent compounds. Yeah, you recognize that one? Usually it's written like that. Let's name it. You could call it dihydrogen oxide, or it could be just hydrogen oxide. This one, this is the structural formula for Monocarbon dioxide. We don't have to use the mono. That's optional. People say carbon dioxide. So straight away we're learning the prefixes. Yeah? Carbon monoxide. Diphosphorus trioxide. Prefix of 2 followed by 3. So what are the prefixes? Hexagonal, 6. Mon, di, tri. Let's do another example. Diphosphorus trioxide. What could I do? CCl4. Let's try and name that one together. Monocarbon tetrachloride, although it's usually just called carbon tetrachloride. Now I don't know if it exists, but if I had the following, I don't know, that would be so you take the name of the element at the end, the one that has is going to have the positive, I guess, valence. Yeah. I don't know how that one works out. Never mind. And we have 2 of those, so we get a neutral compound. And don't worry about these things yet. I'm just giving you the pattern with the prefixes for naming covalent compounds. So that's the way covalent compounds work. But there are exceptions. This one is ammonia. And there would be other exceptions too that I can't think of. Silicon dioxide. So therefore, here's the pattern. When we want to name covalent compounds, covalent means no metals in there. No metals, covalent compounds. Non-metals, bonds or compounds, and here they are: hydrogen, nitrogen, oxygen, sulfur, silicon. But then there are also acids, of course. Let's do the acids. Now I won't do the organic acids. I've covered those to some extent in the organic chemistry lecture. Acids. So to make acids we have a H plus a non-metal. I can take all of the halogens, fluorine, chlorine, bromine, iodine, astatine, and stick a H in front of them and get all the common acids that are have two atoms, diatomic. Hydroiodic acid, hydrobromic acid, so you get the pattern. Now we also get acids making polyatomic ions, so get this into your head and I'll deal with these guys next. What else is there? What else? Okay. Now, if I put a H in front of this, and I'll do this one first. Now, what are polyatomic ions or radicals? They are groups of atoms that behave as a unit in chemical compounds. Let's make the acids first. HSO4, well, it's not balanced. H is positive 1, so I need 2 hydrogens to balance the negative 2. And I get sulfuric acid. Let's see, what else? I'm not sure of the names of some of these though. Okay, if I take a hydrogen with a positive 1 valence, I only need 1 hydrogen and I get HNO3. This is nitric acid. Sulfuric acid and nitric acid. Let's look at this radical here. I need 1 OH radical for 1 hydrogen atom. Of course, I get it straight away, HOH, which is not an acid, it's water. And it's neutral, okay? So, common acids, here's the chlorate radical, carbonate radical, carbonic acid, this one would make. Let's do an unusual one. This is the cyanide radical. HCN is a seriously toxic acid, okay? It's called prussic acid. It crops up in Sherlock Holmes all the time. We'll drop that in your dead in a second. Okay, so these are the polyatomic ions. Now let's do something else. We'll skip away from the acids and then we'll make compounds with these guys, and this time we'll take a metal with them. Before we do that, we'll look at salts. Now to name salt, we take the name of the metal and the non-metal, and we go like this. We'll take the metal sodium +1 and Cl -1, where these are the valences, and we get sodium chloride. Lithium, sodium, potassium, rubidium, cesium, and francium all will behave like this with chlorine, okay? Also with bromine. Chlorine, bromine, all the halogens will behave the same way. 1 and 1, 1 and 1. So, fluorine, chlorine, bromine, iodine, and astatine. And they make fluorides, chlorides, bromides, iodides, acetides, I guess. I never heard of them, but I'm sure they exist. Now we'll go into the next column. The next column behaves differently when we're dealing with chemical bonds. We have magnesium and calcium. Magnesium, calcium, and all the elements in that have a valence of +2. So we're going to need 2 chlorines to make a neutral atom. Yes? And we will get also fluorides, chlorides, bromides, iodides, and acetides using all of these. We need 2 of each of the halogens to make a neutral atom. Valence +2 and valence -1 means we need 2 of these guys to make a neutral atom. Let's do something slightly different. Nitrides. Okay, nitrogen is, I guess, -2. And magnesium is +2, so the formula for magnesium oxide is just magnesium, MgO. Carbides. Now I don't know, I'm not sure, but I think magnesium is going to make a compound of Mg2C magnesium carbide. I'll leave that one out, I'm not a chemist, so I'll just kind of skip that one. Let's take nitrogen and make nitrides. What would that be? Na3N. No, let's skip that one because once again I'm not a chemist. I'm not sure of some of those compounds. So to name salts, this is what we do. We take the name of the metal, the non-metal coming afterwards, and just call it oxide. Oxygen becomes oxide. Nitrogen becomes nitride. Sulfur becomes sulfide. Magnesium, sulfide. Calcium, sulfide. Okay? And that's the way we name compounds. This one will make sulfates, and this one will make sulfites, nitrates. I'm going to talk about this one in a minute. Chlorates, carbonates, bicarbonates. Bicarbonate, for example. One sodium atom is sufficient to make a neutral chemical compound with the bisulfate radical. Sodium bicarbonate, okay? I wrapped up a lot of compounds. I left out some of the weird ones. Let's do some weird ones actually. The transition metals, such as iron and tin, can make multiple different types of compounds. They're multivalent. Let's do a couple. Now we ask ourselves, what is going to be the valence of tin? This is tin in this compound. Well, chlorine, as we know, is -1. And we've got two of them. So the valence is going to be +2. Right? For two chlorines, to neutralize and have a neutral compound, stannous chloride. Okay, let's try another one. We ask ourselves, what is the valence of tin in this particular compound? I'm going to have 4 chlorines, each with a -1, so this must be +4. So it's got a different valence than the previous ones. This happens with the transition metals. Let's do another one. Now there is such a thing called ferrous sulfate. It's a green crystal. Ferrous sulfide, sometimes called iron sulfate. And that's its formula. I wonder, is it? Yeah. So the valence of iron in this is going to be +2. Ferrous sulfate. Let's do ferric sulfate. Now the formula for ferric sulfate, what is it going to be? Fe2SO43. So we have 3 of these guys giving me a -6. 2 of these guys, each with a -3 would be a -6. So this valence would be +3, I guess, in this case, to get ferric sulfate. You can get ferrous chloride and ferric chloride. Okay, and so on and so forth. And so on for the nitrates, ferrous, nitrate, ferric, cuprous. I'm not sure. Is it CuSO4? Yeah, it's cupric. What's the valence of copper in this case if this is -2? And I have two of these. But the answer is +1. Two +1s will neutralize -2. What's the valence of copper in this one? Remember, this is -2. This must be +2. Cupric sulfate. Okay. Now we'll just go to some reactions. That's a lot of chemistry. Let's do a common reaction. How did we get the salts in the first place? Well, maybe acid rain rained down on a metal, all right? And what we do is we get a reaction. Or maybe acid rain came down into a pond which was basic, whatever that means. Well, we'll see in a minute. Here is a base. Base is the opposite to an acid in a way. It carries the OH radical in it, right? Now, what happens when we throw an acid in here? This is seriously dangerous stuff, by the way, Drano. It comes in pellets, but when you make a solution out of it, if it falls on you, it'll burn your skin just like any acid, even worse sometimes. Well, the general rule is an acid plus a base gives me a salt plus a water. And the general rule is that an acid plus a metal is a salt, e.g. Now that's how you make hydrogen in a lab, by the way. You throw a metal onto an acid onto a metal, and you get a salt plus hydrogen gets released. Now, this actually has a formula H2, and I want to speak about that in a minute, right? Because hydrogen does not exist as a single single atom. And how do we deal with this? It doesn't look like it's right. One hydrogen over here, and suddenly I've created one over here. Well, the secret is we end up learning how to balance that as an equation. We'll show you that skill in a minute. First of all, we do some acid-base reactions. Well, the base example I gave you was sodium hydroxide. We're going to get the water first. Okay, this gets displaced. So we get the chlorine part comes in front of here, and the hydrogen part comes in front of here. Okay? There's our salt and there's our water. Let's do it for sulfuric acid. Now this is going to be potassium hydroxide. This one is sodium hydroxide. OH, anything with OH in it makes hydroxides. Now water has OH in it, but it also has the acid part in it. So they fight each other and make a neutral compound. Here we go. So we'll take the SO4 radical on its own. Remember, it's -2. And the potassium will go in front of it. Now potassium has +1, so I'm going to need 2 of them in front of this to make potassium sulfate. And the H2 goes in front of this one. and we get water once again, and straight away we see there's something wrong. There are 3 hydrogens over here, and there's only 2 of them here. Has one vanished? No, we have to find a way to solve that problem, and we will in the next class, not this one. Okay? So acid plus base gives salt and water, acid plus metal gives salt and hydrogen. I want you guys to go away with the acids that I've given you and try and make some reactions. Just make them up. Play around with the equations. You're going to get the metal and the non-metal part. Do you make the salt, and then you're going to get the water itself, okay? Salt and water. The neutralization reaction, in a way. Acid plus base gives a neutral stuff, salt and water. We'll talk about that next time.